Today's topic is specific heat of gases. Unlike solids, in solids we heat a substance and we raise its temperature, and the quantity of heat that we put in is given as mCp, m specific heat into dt. This specific heat is constant, doesn't depend upon anything, because solid has no other state other than just a solid state. But this is not the case in gases. Gases have different states. You can heat a gas under constant volume. You can heat a gas under constant pressure. So the specific heat in each case is different. Here it is different, here it is different. So before we launch into the topic of specific heat of gases, let's examine some terminology that we come across. One term is isothermic. What does isothermic mean? Iso means same, thermic means temperature. So it is a process carried out under constant temperature. Another is adiabatic. This is a process in which no heat is added or taken out of the system. I mean, in a layman's term, you can say it is totally thermally insulated. Next is isobaric. Iso means same, baric means pressure. So this is a process carried out under constant pressure. Another term is isochoric. Iso means again same, choric means volume. So this is a process carried out under constant volume. Okay. Another is Cp. This is molar specific heat under constant pressure. When you heat a gas under constant pressure, the specific heat to be used is Cp. And this heat is in terms of molar and not in terms of simple weight, as we saw in case of solids. Similarly, Cv is molar specific heat under constant volume. When you heat a gas under constant volume, the specific heat to be used is Cv. Then, this is as far as terminology is concerned. Then there are certain relationships, which is Cp minus Cv is equal to R. R is our universal gas constant. And Cp is always greater than Cv, because while heating under constant pressure, the amount of heat that you have to put in is more than what you put in while heating a gas under constant volume. Cp by Cv has a particular terminology called gamma. This is called gamma is Cp by Cv ratio. Now there are very interesting relationships, and which is that if you have a monoatomic gas, what is a monoatomic gas? Gas having only one atom means the atoms are not joined to produce a molecule. For example, helium, neon. Then there are diatomic gases, where gas atoms are two atoms combined to make a molecule. That is why we call it diatomic gases. Examples are, for example, almost oxygen, nitrogen, chlorine, etc. They're all two atoms are combined to make one molecule. Now for monoatomic gases without vibration, Cv is equal to 3R by 2. Their empirical relationship. Cp is equal to 5R by 2, and gamma, which is the ratio of Cp by Cv, is gamma. So if we divide this by this, we get gamma, which is 5 by 3. Similarly, diatomic gases without vibration, Cv is equal to 5R by 2, Cp is equal to 7R by 2, and gamma is 7 by 5. Now, if you have diatomic gas with vibration, this happens when you take an ordinary diatomic gas, and if you take it to very high temperature, then there is another degree of freedom that is invoked, which is vibration. In such a case, the Cp-Cv changes. Cv is given as 7R by 2, Cp is given as 9R by 2, and gamma is 9 by 7. Now, for adiabatic process alone, there are certain relationships, which is, if we take a relationship between P pressure and volume, the relationship is PV power gamma is constant. If we take relationship between P pressure and temperature, the relationship is T power gamma divided by P power gamma minus 1 is constant. If we take volume and temperature relationship, then it is TV gamma minus 1 is constant. Now, if we take one in an adiabatic process, some work is done by the gas which is given as P1 V1 minus P2 V2 divided by gamma minus 1. We will see the derivation just now. We know from thermodynamics that du is equal to dq minus dw. This is the change in internal energy this is the heat supplied to the system. And this is the work done by the system. Okay. This implies that du is equal dq. dq is equal to du plus dw is equal to du plus pdv. Because what is the work done by the gas? Work done by the gas is pressure. For small changes, the work done is pdv. This is equal to du under constant pressure plus we know PV is equal to nRT. If we make pressure constant, then differentiating both the sides, what will get? PdV, N is constant, R is constant, we get dt. So PdV becomes nR dt. So this PVdV becomes nR dt. Okay. Now we know that in case of du, we know du is equal to dq. This is minus dq, sorry, it's okay. dq is equal to this plus this is all right. So du is equal to dq minus dw. Now, if we take it under constant volume, what was this? This was pdv. So under constant volume, this term goes away. So what you left is du under constant volume is equal to dq under constant volume minus 0. Okay. Now we also know that du only depends on temperature. Change in internal energy only depends upon temperature, which means du at, whether we take du at constant pressure or we take du at constant volume is same. And this will imply that dq under constant pressure is equal to du under constant volume plus nR dt. This relationship we derive out of this relationship, wherein dP is replaced by dV, du under constant pressure. Du under constant pressure is replaced by du under constant volume using this equation. Okay. So if we take this, what is this? dQ, external heat that we put in under constant pressure, is nothing but NCP dt. Similarly, under constant volume, this will become NCV dt. Right? So what we get is, if we integrate Cp, or if we just knock it off, NCP is equal to NCV plus NR, or simply Cp is equal to Cv plus R, or Cp minus Cv is equal to R. This is a very, very famous relationship, as we saw earlier here. This one, Cp minus Cv is equal to R. Cp minus Cv is equal to R. Now, du under constant volume is equal to du under constant pressure is equal to q dq under constant volume. So we have already seen that change in internal energy under constant volume or constant pressure, both are same. And if we take this one, this is equal to this, because PdV in that case is 0. So what we get is, if we write it separately here, dq is dependent only on Cv dt. Now for work done under adiabatic condition, we have seen that work done is equal to PdV. Yeah. This is for small volume change in volume, but if there is, we go from end to end. This is from volume V1 to volume V2. P we can replace by because we know PV to the power gamma is constant. So P can be replaced as some constant time V to the power gamma. So putting the value of P from here in this equation, we get P is replaced by K by V to the power gamma here. To dV. And if we integrate, what we get is K power KV 1 minus gamma where V goes from V1 to V2, which is also equal to V2 gamma minus 1 minus K V1 gamma minus 1. This is also written as, we can change the signs. These signs we can change. So what we get is gamma minus 1 this is by replacing replacing V by R, V by P in this case. V we replace with P. Comes like this. So work done in adiabatic process is equal to this one. And the last thing is that internal energy is only dependent upon temperature, and which is also given as NCV. This is in the absolute terms of, this is internal energy. All along we had seen, we've been talking about change in internal energy, but this is absolute total internal energy, which is given as NCV, an absolute temperature of the gas.